You're it.
Hi, I'm Galila Azarez, and welcome to the dangerous world of pre-calculus, Part 1. I hope that opening chase scene really got your adrenaline pumping, because the next 2 hours are going to expand your pre-calculus and algebra comprehension exponentially. We'll review the basics of polynomials, tell you all about rational functions, assess asymptotes, and solve systems of equations and inequalities. For each concept, we'll show you plenty of examples, and when we're through, you'll have enough cool math weapons in your arsenal to face any dangerous pre-calculus situation with deadly confidence.
And now, it's disclaimer time! To truly absorb the intricacies of pre-calculus, you must attend your classes, read your textbooks, and listen to your professors! So go to class!
Ahem. While we are running disclaimers, I would like to add that although the standard deviants do not take themselves very seriously, they take their academics extremely seriously. Okay? So you can rest assured that the information presented herein is PhD endorsed.
One last thing. This pre-calculus part 1 video assumes that you know the information presented in college algebra parts 1 and 2, including basic algebraic tools and concepts like functions, graphs, and other features of polynomial expressions. You should also know how to put linear and quadratic equations in standard form, multiply binomials, and how to factor these expressions and graph them on the coordinate plane. Not that we want you to buy our standard deviants college algebra tapes for a review or anything like that.
Pre-calculus is great. Pre-calculus is the best. If I keep watching this tape, I'm sure to get there. Not just I said it ain't. Yeah, pre-calculus is great. I'm getting the day. What a sweet day when I come home.
Part 1, Rational Functions.
Section A, Review of Functions and Polynomials.
It's review time.
Okay, time to buckle down. You remember the idea of an algebraic function. A variable appears by itself on one side of an equation with one or more other variables on the other side. Like y equals 4x minus 1 and z equals 3x plus 5y. Whenever you see an equation like this, we say that the solo variable is a function of whatever variables appear on the other side of the equation. So when y equals 4x minus 1, y is a function of x.
As soon as we know a numerical value for x, we can substitute it into the equation to compute the corresponding value for y. This process is called evaluating the function. It illustrates the general concept of a function, that for each choice of the independent variable x, there is one and only one corresponding value of the dependent variable y. The equation tells us exactly how to determine that y value. In the case of the equation, y equals 4 times x minus 1, if x equals 3, then y equals 4 times 3 minus 1, or 12 minus 1, 11.
Sometimes, to emphasize the fact that you're dealing with a function, the letter y is replaced by f of x, shorthand for a function of x. So the equations y equals 4x minus 1 and f of x equals 4x minus 1 are really interchangeable in most cases. Also, any other letter can be used in place of f. For example, you could see the equation y equals 3x squared minus 7 expressed as g of x equals 3x squared minus 7.
There are different kinds of functions, grouped into various categories. One main category is polynomials.
Polynomials?
Polynomials are functions that can be expressed as combinations of coefficients, variables, and exponents. Some examples of polynomials are 5x squared, 4x cubed minus 6x plus 5, and x to the 11th power minus 3.4x squared plus 1/2. Remember, the coefficients are constants, or any real numbers. The variables are letters, and the exponents have to be whole numbers.
One way to think about polynomials is this. Given a value for x, you should be able to figure y using only addition, subtraction, and multiplication. If there is division anywhere in the calculation, it only involves fractional constants that are coefficients, like 1/2. So it should be no surprise that polynomials can be added, subtracted, and multiplied. And the result is always another polynomial. These results can be put into standard forms, graphed, evaluated, and generally manipulated. You should be pretty up to speed on those operations from college algebra parts 1 and 2. But if you're still a little hazy, it's not too late to pick up those first 2 tapes for a little review.
Section B, Rational Functions.
As we mentioned, polynomials make up just one category of functions. Now we are going to look at a different category in which you create functions by dividing two polynomials.
Dividing two polynomials.
Now, you may remember from arithmetic in grade school.
Now class, there are several ways to writing division of whole numbers. For instance, if you are dividing 21 by 7, you can either write it as 21 divided by 7, 7 into 21, or as a fraction, 21 over 7. This way of writing division is also called a ratio, which is why numbers written as fractions are called rational numbers.
Polynomials basically behave the same way as those grade school fractions. When you divide two polynomial expressions, you write them like a fraction or a ratio. These functions are called rational functions, and they look like this. But more often you'll see them like this.
X squared minus 5x minus 6 over 4x minus 1. To emphasize that this is a function, we need only to put it into standard form by setting it equal to f of x. Some other rational functions are g of x equals x plus 2 over x minus 1, and h of x equals 2x squared plus 5x plus 10 over x squared plus 4x minus 2. Like with numerical fractions, the top of a ratio of polynomials is called the numerator, and the bottom is called the denominator.
I'm the numerator.
I'm the denominator.
And I'm the terminator.
I'll be above.
I'll be below.
And I'll beat back.
The standard formula for rational functions looks like this. F of x equals h of x over g of x. It looks spooky, I know, but it's not. H of x and g of x are just basically code for a polynomial function and another polynomial function.
But rational functions don't always appear in this standard form. Sometimes they come up in an algebra problem in disguise. Your tip-off is that if you see a variable in the denominator, you must know that most likely you're dealing with a rational function, like this example. The x and y in the denominators tell you these are rational functions.
In your pre-calculus studies, you'll be asked to solve rational function equations and often multiply, divide, add, or subtract them from each other. But how do you do it? Simplify. I pity the fool who must simplify rational functions.
Don't worry, neighbors. I'll help you. We'll start by looking at multiplication and division, because multiplication and division are easier. Thanks for being here with me today. Now please excuse me for just a moment. I have to go place a bet on a monster truck rally.
Section C. Multiplying and dividing rational functions.
You can operate on rational functions just the way you can on any other ratio or fraction. And multiplying two rational functions works the same as multiplying two fractions. Remember how to do that? Right. Just multiply across. You do the same thing with rational functions. Of course, the tops and bottoms of rational functions are polynomials. So to multiply them, you have to use FOIL.
You mean I must foil an evil plan for world domination?
No.
Class, when you multiply polynomials, you multiply in terms of which order?
First, outer, inner, last.
Very, very nice. You all get A's.
For example, multiplying the functions x plus 1 over x plus 3 and 2x plus 3 over x minus 2, we get 2x squared plus 5x plus 3 over x squared plus x minus 6.
Hey, slow down!
Well, although foiling gives you the standard form for a rational function, it is often easier to simplify if you leave the function in factored form. In fact, sometimes the top and bottom start out in a form that can be factored. Give us an example, deviants.
Multiply x squared minus 4 over x minus 3 by x squared minus 4x plus 3 over x squared minus 2x. But before doing the multiplication, factor all of the tops and bottoms of the fractions. You see that some factors, like x minus 3 and x minus 2, end up on both the top and bottom of the fraction. This means you can simplify them by canceling them, like reducing to lowest terms. For a final answer, you can either leave it in factored form or put it in standard form, x squared plus x minus 2 over x.
Which I can assure you is considerably simpler than multiplying the whole business out. To summarize, it is easier to multiply two rational expressions if each expression is factored as far as possible in the first place. Next issue, division.
Dividing two rational functions also works the same as dividing two rational numbers. You know that to divide is just to multiply by the inverse, aka the reciprocal. This whole process is also known by the rule invert and multiply.
Invert.
And multiply.
Invert and multiply.
For example, dividing x plus 1 over x plus 3 by 2x plus 3 over x minus 2 is the same as multiplying x plus 1 over x plus 3 by x minus 2 over 2x plus 3, which is the reciprocal of 2x plus 3 over x minus 2. So dividing x plus 1 over x plus 3 by 2x plus 3 over x minus 2 gives us x squared minus x minus 2 over 2x squared plus 9x plus 9.
You'll also have to be able to recognize the division operation when it looks like this, a compound fraction. That means the problem we just worked could look like this compound fraction, x plus 1 over x plus 3 over 2x plus 3 over x minus 2. So easy, of course. Anytime you see a compound fraction like this, just remember that it's a division. The fraction on top is being divided by the fraction on the bottom. So you can just put the expressions beside each other to get the more familiar form, then invert the second term and multiply it out to get the answer. Exactly like we just did.
Remember, when your function reaches division junction, don't hesitate to reciprocate.
That pretty much covers multiplication and division. Pretty easy, huh? Now comes the tricky stuff. Let's add and subtract.
Section D. Adding and subtracting rational functions.
When adding and subtracting two rational functions, you must have a common denominator. Just like when adding or subtracting fractions. Remember that from grade school?
Okay, class, let's find a common denominator so we can add 3/5 and 4/7. The common denominator is 35. And our answer is 41/35, or 1 6/35. Okay, class?
Hope you enjoyed that trip down memory lane. Now let's add two rational functions. Here we've got x plus 1 over x plus 3 and 2x plus 3 over x minus 2. Before you can add these, first you have to find a common denominator. Usually it will be the product of the denominators of the two ratios you are trying to add. So to find the common denominator, you just need to multiply the denominators. After you multiply, the common denominator will be x plus 3 times x minus 2.
Now we have to rewrite each of the original rational functions using the common denominator. You know how changing denominators works for fractions. You can multiply both the top and bottom of a fraction by the same number without changing the actual value of the fraction. You remember this from grade school, too. Class, you know 2/3 is equal to 2/3 times 1. And you know 1 is equal to 4/4. So if you multiply 2/3 by 4/4, you get 8/12, which equals 2/3. In the same way, you can transform a rational function if you multiply it by an expression equivalent to 1. In this case, we want the new denominator to be x plus 3 times x minus 2. So we have to multiply the first function, x plus 1 over x plus 3, by the denominator of the second function over itself, x minus 2 over x minus 2. The same thing for the second function, multiplied by the denominator of the first function over itself, x plus 3 over x plus 3. Let's look at that again in slow motion. All you're doing is multiplying each part by whichever one of x plus 3 and x minus 2 isn't already in the denominator. Now you have an answer in factored form, but since you want it in standard form, you use the FOIL method to multiply the factors on the top and bottom of each fraction. FOILing gives you x squared minus x minus 2 over x squared plus x minus 6 plus 2x squared plus 9x plus 9 over the same denominator, x squared plus x minus 6. Finally, we can combine the like terms on top, leaving us with 3x squared plus 8x plus 7 over x squared plus x minus 6. And that's your answer.
Okay, quick recap. We started with two rational functions, added them together, and then put the answer into standard form. Fine, but remember the standard form is not necessarily the most useful form. Often it helps to factor both the top and the bottom of the rational function. We won't review factoring here because we know you already know it from college algebra. But keep in mind the common denominator we used above started out in the already factored form x plus 3 times x minus 2, and it's much easier to see simplifications and cancellations when equations are in factored form. So, we can use either x squared plus x minus 6 as the denominator or x plus 3 times x minus 2. Either form is correct.
You already know that the process for subtraction works exactly the same way, since subtraction is really just negative addition. But here's a subtraction example anyway, to give you another spin on common denominators.
Take the problem 2x over x squared plus x minus 2 minus x squared over x squared plus 5x plus 6. This time, before we form a common denominator, let's try factoring each denominator. You know from our first video how to factor, so you should find that x squared plus x minus 2 factors to x minus 1 and x plus 2, and x squared plus 5x plus 6 factors to x plus 3 times x plus 2. so we can rewrite the original problem with the factored denominators.
Do you ever notice how profs can make problems look harder than they actually are? Sometimes, inside a problem that looks really hard, you can find a trick that makes it lots easier. One of these tricks is by factoring or simplifying the problem. So be on the lookout!
No doubt you have already observed that both fractions already have in common a factor of x plus 2 in the denominator. That's nice because it means you don't have to multiply either fraction by that factor. X plus 2 only has to appear once in the common denominator. That means the common denominator we need is x plus 2 from both fractions times x minus 1 from the first fraction times x plus 3 from the second fraction. So, following the same methods we just used, we will multiply the top and the bottom of the first rational expression by x plus 3 and the top and the bottom of the second rational expression by x minus 1. Why? Because those are the parts of the common denominator that each function is missing.
Next, we put each rational function into the standard form, which requires FOILing, or multiplying, the top and bottom of each expression, as you see here. Then we combine the numerators, keeping the common denominator, which gives us a final answer in standard form of negative x cubed plus 3x squared plus 6x over x cubed plus 4x squared plus x minus 6. The numerator factors as x times the quantity negative x squared plus 3x minus 6, and the bottom appears in its original form of x plus 3 times x plus 2 times x minus 1.
Now we have looked at each of the 4 operations in isolation, but of course some problems you run across in rational functions will require combination of operations. Here's a typical example.
Simplify the following expression: 1 plus 2x plus 1 over 2x minus 1 over 1 minus 2x minus 1 over 2x plus 1. This is a compound fraction, so it's a division problem. And this is a compound fracture, but that's not important right now. Normally, we would invert and multiply. But that requires the top and bottom to be in a standard form. So the first step in this problem is to put the top and bottom into a standard form.
Now, the top and the bottom involve addition and subtraction. So to put each into the standard form, we need common denominators. We will do each part separately, beginning with the top part of the main fraction, 1 plus 2x plus 1 over 2x minus 1. Rewrite the 1 as a fraction with the same denominator. Then add across the numerator. You get 4x on the top, so the answer here is 4x over 2x minus 1.
The bottom of the main fraction works out in the same way, setting 1 equal to 2x plus 1 over 2x plus 1, and simplifying to 2 over 2x plus 1.
Now we can use these in the original problem. To do the division, all you do is invert and multiply.
So here goes. The final expression, 4x squared plus 2x over 2x minus 1, is the standard form for the rational function. The next to the last expression, 2x times 2x plus 1 over 2x minus 1, has the top and bottom factored and is also an acceptable answer.
Section E, Graphing Rational Functions.
As you know, a graph can give you a lot of information about a function. Graphs of normal polynomials are always unbroken lines or smooth curves.
But, as you will soon see, rational functions can sometimes have breaks, separating the graph into 2 or more disconnected pieces. These breaks are called discontinuities, and we're about to explore what causes them.
Polynomials have no breaks or discontinuities because polynomials only involve addition, subtraction, and multiplication. These are all perfectly safe operations and can never cause you any difficulties. But, unlike polynomials, rational functions involve division, which is not always a safe operation. In fact, there is one situation in which division is not only unsafe, it's impossible. You cannot divide by 0. No one, not even the guru on the mountain, can divide by 0. In terms of fractions, this means you cannot have a fraction with a 0 in the denominator. Never! Not ever! We've seen that the standard form for a rational function is a fraction with a polynomial on the top and one on the bottom.
Rational is poly on the top and poly on the bottom.
That means that you're dividing by something that is a variable quantity. And since you don't know the value for x, you can't be sure of the value on the bottom of the fraction.
Mom always said variable in the denominator's like a box of chocolates. You never know what you're gonna get. So it's possible that some value of x will lead to division by 0. If so, that value is straight up off limits as far as the rational function is concerned. Example, if f of x equals x plus 2 over x minus 1, then when x equals 1, the function value becomes 1 plus 2 over 1 minus 1, which is 3 over 0, with 0 in the denominator.
That's no good.
For this function, choosing x equals 1 is a bad idea.
Bad.
When there's a bad choice of x, one that makes the bottom of a rational function 0, it shows up as a break in the function's graph. For example, suppose you're trying to graph f of x equals x plus 2 over x minus 1. Say you start out by inserting 0 for x. So now you have y equals f of 0, which equals 2 over negative 1, or negative 2. So, you put a point down on the graph at 0, negative 2. So far, so good. Next you try x equals 1. This time you get y equals f of 1, which equals 1 plus 2 over 1 minus 1, which equals 3 over 0. That, as you know, is impossible, and it means that you cannot compute a y value when x equals 1.
Really bad.
It also means that the graph of this function will not have any point for x equals 1. There will be points to the left of x equals 1, like at 0.9 and 0.99, and points to the right at, say, 1.1 or 1.01, but there cannot be a point on the graph exactly at x equals 1. That is what shows up as a break, or discontinuity. The graph is separated into two disconnected pieces at x equals 1.
Now, rational functions don't always work this way. Take the graph of f of x equals 1 over x squared plus 1. Notice that for this case, no matter what number you choose for x, the denominator will never come out to be 0. Observe that the graph is smooth and unbroken. Don't forget that, as a general rule, when you deal with rational functions, you must expect the possibility that the denominator might turn out to be 0.
Did you get that? Okay, let's review. For a polynomial, the graph is a smooth, unbroken curve. But for a rational function, some values of x might lead to a 0 in the denominator. That is an impossible situation because there is no y for such an x. At that point, there's no value for the function and there's a break in the graph. Bang! Cool beans!
A break can show up in one of two ways. The simpler type of break is just a missing point on the graph. This function is an example of this type of break. Y equals x squared minus x minus 6 over x minus 3. The graph looks like this. The gap that appears in the graph is at the point where x equals 3. If you try to substitute 3 for x in the equation, the result is y equals 0 over 0. That's not possible, not feasible, and not allowed. So there is no y for x equals 3. This is a typical example of the missing point syndrome, and conveniently, it always goes with a result like 0 over 0.
When you see a result of 0 over 0, it also tells you that it should be possible to factor the top and bottom of the rational function and simplify. In the example at hand, the top factors to x minus 3 times x plus 2. The x minus 3 on the top cancels with the bottom, so the whole function simplifies to y equals x plus 2.
For this kind of a break, the missing point is kind of a loophole or technicality. For the original function without simplifying, x equals 3 is a bad point because it leads to division by 0. But if you simplify first, then there's no problem with x equals 3. Although this isn't that common in practice, it turns out to be one of the key ideas in calculus. Not that you'll ever take any more math after this pre-calc business, but...
Hey, wait a minute. Math is fun. It's the kind of thing you should practice your whole life, especially when your cable is on the fritz.
So that's the lowdown on the first kind of break in a rational function graph, known to math heads as a removable singularity.
In contrast to the unremovable plurality, which for all intents and purposes doesn't exist. But that's not important right now.
Removable singularity appears simply as a missing point on the graph and occurs when putting in a number for x leads to 0 over 0. For this kind of break, if you factor and simplify the rational function, the division by 0 can be avoided. Now let's take a look at the second kind of break.
Section F. Asymptotes, an introduction.
What is the second type of break in a rational function? Is it a coffee break? No! How about a shake and break? No!
Thanks, Mom.
No. We're talking about a break where you find a new graph feature called an asymptote.
Look here at this graph of f of x equals x plus 2 over x minus 1.
At the point where x equals 1, there is no y value because the 0 appears in the denominator. But what happens at an x value that is nearly equal to 1? Well, if x equals 1.5, then y equals 1.5 plus 2 over 1.5 minus 1, which is 7. If x equals 1.4, which is even closer to the bad point, we get y equals 1.4 plus 2 over 1.4 minus 1, which equals 8.5. At x equals 1.3, y equals 11. At x equals 1.2, y equals 16. And at x equals 1.1, y equals 31. As these data points show, if x is just slightly more than 1, y is pretty big. And the closer x gets to 1, the bigger the y. If you extend the graph higher towards the top of the diagram, the curve becomes an almost straight vertical line. So this is what we've been looking for. When a graph appears to extend out so that it nearly lies right on a straight line, that line is called an asymptote.
For our example, so far we have only examined the graph on the right side of the break. But let's check out the other side.
As before, we'll see what happens when x is near 1, but this time we will choose values that are less than 1. For x equals 1/2, we find y equals 2.5 over negative 0.5 equals negative 5. For x equals 0.6, y is negative 6.5. For x equals 0.7, y equals negative 9. For x equals 0.8, y is negative 14, and when x equals 0.9, y is negative 29. This time the curve is extending downward along what looks like the same vertical line.
So, looking at the graph as a whole, you see there are two separate parts. Starting from the left, the curve extends over and down, essentially turning into a vertical line that runs off the bottom of the graph. Theoretically, the graph will keep going down forever without ever reaching an endpoint and without ever crossing the vertical line x equals 1. The other part of the curve starts out infinitely high above the graph and comes down along what is essentially a vertical line, sloping off at the right as it nears the x-axis. There are two parts to illustrate the second kind of break in the graph of a rational function. For this kind of break, the two parts of the graph will sidle up beside the vertical line, called the vertical asymptote. Each part of the graph will stay on its own side of the line and will never actually touch the line, but will either extend infinitely up or infinitely down.
Other graphs with vertical asymptotes may both turn up, both turn down, or one part can go each way, as with the first example.
Asymptotes come in different flavors. The kind we just saw is a vertical asymptote. Vertical asymptotes always occur at a break in the graph and are associated with a denominator that equals 0. But a graph may also straighten out along a straight line that is not vertical. In such cases, there may not be a break in the graph, but as the graph extends to the far right or far left, it should appear to straighten out.
The example we saw before looks like this. Observe the graph.
When the graph is extended in the direction of positive infinity on the x-axis, you will observe that it becomes a straight line, hence the expression straighten up and fly right. On the other hand, if the curve is extended in the direction of negative infinity on the x-axis, then it will straighten up and fly left. Do not confuse these with straighten left and fly down or straighten right and fly up. Any questions?
Sir, I have a question. Why do we go to foreign countries and get involved in meaningless civil squabbles?
Grunt! I will have no politics while I'm teaching algebra. Drop and give me the square root of 625 push-ups. And if you ask me how many that is, you have 5 squared more.
In this example, the asymptotes that appear to the left and right lie along a horizontal line, so they're cleverly called horizontal asymptotes.
Horizontal.
Asymptotes.
Horizontal asymptotes.
Okay, review time. Graphs of rational functions differ from polynomials in a couple of ways. Breaks occur whenever there's an x that gives us 0 in the denominator. That's the bottom of a rational function. Maybe the break is just a missing point from the graph, in which case the same value for x will also make the numerator. That's the top of the fraction, 0. So you'll have 0 over 0, and you should be able to factor and simplify the rational function. However, if a break is not just simply a missing point, then it will occur as two parts of a curve extended up or down to infinity, approaching but never touching the sides of a vertical line. This is your vertical asymptote. Graphs can also have horizontal asymptotes. These occur when the curve straightens out along the horizontal line that extends to the right or left.
Hey man, so what?
So what? Alright, compadre, here's the deal. You need to generally comprende the kinds of graphs that can appear for rational functions. And not only do you need to know what kind of features you're going to see, you'd better be able to identify exactly which features occur where. Bottom line, you need to find where your asymptotes are at. And you're about to find out how to do just that. That's what. These things will kill you.
Section G. Finding asymptotes.
So, how do you find where a rational function has asymptotes or where the function breaks? You must put the rational function into a couple of different forms.
You know the standard form for a rational function. For example, y equals x squared minus x minus 6 over x squared minus 4 is in the standard form.
A second, very useful form for functions is found by factoring both the top and the bottom of the fraction.
For our example, that leads to y equals x minus 3 times x plus 2 over x minus 2 times x plus 2. As we know, the factored form helps simplify the rational function. With our example, we can reduce this function to y equals x minus 3 over x minus 2. This factored form will reveal the locations of two crucial features of the graph of this function: vertical asymptotes and x-intercepts. Also, when we cancel the x plus 2 out from the top and bottom, we should note that the original function has a missing point type break at x equals negative 2.
Once the fraction has been reduced as far as possible, any roots of the denominator will equal your vertical asymptotes, and any roots of the numerator will give you the x-axis intercepts. For y equals x minus 3 over x minus 2, there is one x-intercept at x equals 3, and a vertical asymptote at x equals 2. You observe this in the graph. So, issue number 2, a more involved example.
Since the top and the bottom of this function are already factored, we can easily find the root for both. You remember how to find roots, don't you? The root is where x is. Find the x, and you found the root. Taking the numerator 2x minus 1 times x plus 2, first we set each factor to 0. If 2x minus 1 equals 0, then x equals 1/2. And when x plus 2 is 0, then x equals negative 2. These should be points where the graph crosses the x-axis.
So let's check out the denominator x times x minus 2. We find the roots the same way, by setting x equal to 0. Conveniently, the first root here is the easiest root in the book. When x is a factor, x equals 0 is one root, the other factor, x minus 2, yields 2 as the other root.
Now observe in the graph.
They are vertical asymptotes, where x equals 0, namely the y-axis, and at x equals 2.
So you've got a rule. After eliminating any common factors from the top and bottom, you can find the vertical asymptotes of a rational function where you find the roots of the denominator. And you can find the x-axis intercepts by finding the roots of the numerator. Nice trick, no?
It's nothing.
As for horizontal asymptotes, to find those we can return to the standard form. Remember that these occur as the graph extends to the far right or left. That means we're looking at very large positive and negative values of x. For such extreme values of x, only the highest degree terms in the numerator and the denominator have much effect.
So what's the rule, Mr.?
The name is...
Relax, Radical 49. To determine if there are any horizontal asymptotes for a rational function, put the equation into its standard form, then temporarily eliminate everything but the highest power of x in the numerator and denominator. If those powers are the same as in the example where there were x squareds in both the top and bottom, there will be a horizontal asymptote, and you can find it by dividing coefficients. If there is a higher power below in the denominator, the x-axis itself will be the horizontal asymptote. And if there is a higher power in the numerator, there will not be any horizontal asymptote.
And with the help of a higher power from anywhere...
In the standard form, the function y equals 2x minus 1 times x plus 2 over x times x minus 2 looks like 2x squared plus 3x minus 2 over x squared minus 2x. For a very large value of x, only the x squared terms on the top and bottom will have much effect on the y value. For instance, when x equals 100, the top of the fraction is 2 times 100 squared plus 3 times 100 minus 2, which equals 20,000 plus 300 minus 2. Obviously, 20,000 is much bigger than the other numbers. For an even larger value of x, say 1,000, this effect becomes even more pronounced. Using this idea for large values of x, we can drop lower x values and approximate y from 2x squared plus 3x minus 2 over x squared minus 2x to y equals 2x squared over x squared, which is further reducible to 2 because the x squareds cancel out. That tells us that y will be just about equal to 2 for all points to the extreme left or right on the graph. So y equals 2 is a horizontal asymptote.
That covers most features of graphs of rational functions that you should have to deal with in your class. The graphs can have breaks, vertical and horizontal asymptotes. Different forms of a rational function will tell us different things about the graph. The standard form helps us recognize horizontal asymptotes when the degree on top is less than or equal to the degree on the bottom. The factored form tells us where vertical asymptotes and x-intercepts are.
What is the use of knowing this kind of information? As you all know too well, it's very easy to make mistakes in math. It's even easy to misuse or abuse a calculator or a computer. The best way to check up on your own work is to know at least 2 different ways to do it.
Section H! Sample word problem. All right. Rational functions often occur as algebraic models for problem situations. So let's do a sample word problem for rational functions like the one you'll be tested on.
Our example deals with mixtures. Gums, Radical 49's nemesis who lost his teeth in that skateboard accident, has 50 ounces of a gold alloy that is only 35% pure gold. Gums is making a mold of his teeth to replace the aluminum ones he lost. But Gums, he's a classy guy, so he wants to add some pure gold to this alloy in order to increase the percentage of pure gold to 75%. How much pure gold should he add? Our first step is to find a function that will represent the percentage of gold in the alloy. The starting amount of gold in the alloy is 35% of 50 ounces. 0.35 is 17.5 ounces. Let x equal the ounces of pure gold that Gums will add to the mixture. then 17.5 plus x will equal the number of ounces of pure gold in the new mixture. Additionally, 50 plus x equals the total weight in the ounces of the new mixture. The concentration or percentage of gold in the new mixture equals the ratio of the ounces of pure gold in the mixture and the total ounces of the mixture. If we let C of x represent the concentration of gold in the new mixture, then C of x equals the total amount of pure gold, x plus 17.5 over x plus 50, the total weight of the entire mixture.
Let's stop here and take a closer look at this function, starting with a computer graph of the function. Now let's verify that the graph is accurate using the analysis we discussed earlier. First, because the given form for C of x is already factored, we can see that there will be an x-intercept at x equals negative 17.5 and a vertical asymptote where x equals negative 50. These features are in sync on the graph. Although we will only be interested in positive values of x, what we have seen so far shows us that C of x is positive for any positive x, and will have no breaks for positive x. Had the results turned out differently, that might indicate that there was an error in formulating the equation for C. But seeing no error, it looks like we're good to go.
We're good to go.
Next, we can see that both the numerator and the denominator have a degree of 1. Remember our rule from earlier? If the powers are the same in the numerator and the denominator, there will be a horizontal asymptote, and you can find its location by dividing the coefficients. That means this function will have a horizontal asymptote, which we can locate by approximating C of x using only the highest powers of x. That makes C of x approximately equal to x over x, or 1, for larger values of x. That also makes sense because as we add more and more gold to the mixture, the percentage of gold will gradually increase, but since it started out impure, it can never reach 100%, or 1.
That's why this function has an asymptote of 1.
This information from the graph gives us a pretty good insight about how adding more gold changes the concentration. For our specific question, Gums wants to make the new mixture 75% pure. He must find a value of x so that C of x equals 0.75. That point will appear on the graph where a line drawn straight across from 0.75 on the y-axis strikes the curve. But we can also find the answer using algebra.
Since we want to find the value of x when the concentration, or C of x, is 75%, or 0.75, we replace C of x with 0.75, and there's a rational equation. Now we just need to solve for x to find our answer. Multiplying both sides by x plus 50 to get x plus 50 out of the denominator, we get 0.75x plus 37.5 equals x plus 17.5. Combining like terms and solving for x, we get 0.25x equals 20, or x equals 80 ounces. So Gums must add at least 80 ounces of pure gold in order to make the total mixture at least 75% pure gold. We can check that answer by figuring C of x, plugging in 80 for x because 80 is the amount we got for our answer. Our equation is C of 80 equals 80 plus 17.5 divided by 80 plus 50. Simplifying, we find 97.5 over 130, or 0.75, which is what we wanted.
Give me the gold! Gingivitis cake and sauce, sucker fool! I need it for my T-square!
Looks like you have company.
Where are we gonna go?
We should go back to my room. Listen, there's a little more conducive to studying. I think you got the point.
Nice line.
Part 2. Systems of linear equations and inequalities.
Section A. Solving systems of linear equations.
Up until this point, we've been dealing with single equations looking at one algebraic relation or expression at a time. But often there are situations in the real world and pre-calculus tests that give you more than one expression relating to, or even more than two, variables. When you are given more than one related expression to work with, you have what is called a system of equations or inequalities.
Systems of equations or inequalities.
With a system of expressions, you can obtain more specific information about each of the variables than you could given only one expression.
Here's a way to look at solving systems of equations or inequalities. When you find a solution for one algebraic equation in two variables, like y equals 2x plus 3, you will usually get an answer that is a line or curve on a graph, and any point on that line is part of the solution set for the equation. Well, when you have two equations in a system, your solution set will be the place or places where the solution sets to both equations, that is, the graphs of both equations intersect. If you have two linear equations, the solution may be only one point where the lines of each graph cross each other. If you have a linear and a quadratic equation, there may be 2 points where the graphs intersect. The point is that when you're solving systems, you're looking for solutions that work for all the equations you are given. For an example, let's look at the case of MacDiver and his business, You Fix It, Inc.
MacDiver has a store that only sells bubblegum and Band-Aids.
Hey, you can fix anything with bubblegum and Band-Aids.
When he opens his shop, MacDiver has exactly $90.
Yeah, well, after the show got canceled, things got a little slow.
He used this $90 to purchase the inventory he will be selling in a store. His supplier sells bubblegum and Band-Aids at $1 a pack. From this information, we can figure out how many packs of bubblegum and Band-Aids MacDiver will be able to purchase for his store. If we let X be the packs of bubblegum and Y be the packs of Band-Aids that MacDiver buys, the equation of packs of Band-Aids plus packs of bubblegum that cost $90 would look like this. 1x plus 1y equals 90, or since 1 times anything is itself, x plus y equals 90. He used this $90 to purchase the inventory he will be selling in a store. His supplier sells bubblegum and Band-Aids at $1 a pack. From this information, we can figure out how many packs of bubblegum and Band-Aids MacDiver will be able to purchase for his store. If we let X be the packs of bubblegum and Y be the packs of Band-Aids that MacDiver buys, the equation of packs of Band-Aids plus packs of bubblegum that cost $90 would look like this. 1x plus 1y equals 90, or since 1 times anything is itself, x plus y equals 90.
MacDiver sells the boxes of Band-Aids in his shop for $2 each, and the packs of bubblegum for $3 each. Business is pretty brisk the first day. MacDiver sells out his entire supply of both boxes of Band-Aids and packs of bubblegum, and ends up with $230 in the cash register at the end of the day. We can also use this information to make another different relation between the number of boxes of Band-Aids and the number of packs of bubblegum that MacDiver has in the store. We know that MacDiver sold X packs of bubblegum at $3 each, which can be written as 3X. He also sold Y boxes of Band-Aids at $2 a box, or 2Y, and Band-Aids sold plus bubblegum sold equals $230. We can write this relation as the equation 3x plus 2y equals 230. So, the question is, how many packs of Band-Aids and how many packs of bubblegum did MacDiver buy and sell? Here we have two relations and two unknown values. The first shows that the total cost to MacDiver for Band-Aids and bubblegum is $90. The second shows that his total income from selling bubblegum and Band-Aids is $230. We must find the values for x and y that will solve both of these relations.
There are several ways to solve problems of linear equations, and we'll give you examples of each. One way to solve this problem is to look at the graph of our two equations. You remember from the Algebra 1 tape. that it's easiest to graph an equation when written in slope-intercept form. So we'll put both relations, x plus y equals 90 and 3x plus 2y equals 230, into standard slope-intercept form. This gives us y equals negative x plus 90 for the first equation and y equals negative 3 over 2x plus 230 over 2 for the second. Graphing these relations, we see they form two lines that cross at what appears to be the point 50, 40 on the graph. Conveniently, the point where these two lines cross is the solution to the system.
That's very nice.
This means that 50 plus 40 equals 90, and 3 times 50 plus 2 times 40 equals 230, where 50 is the value for x and 40 is the value for y. Remember, the packs of bubblegum are represented by x, and packs of Band-Aids by y. So from this graph, we know that MacDiver must have bought 50 packs of bubblegum and 40 packs of Band-Aids to start with.
But graphing is not the only way to solve a system of equations like this. There are also some ways to solve systems of equations algebraically.
In order to solve an equation algebraically, you have to have the same number of equations as you have variables. And remember, variables are unknown values.
In the case of our problem with MacDiver, we have two unknown values, packs of Band-Aids and bubblegum, and two equations, which you see here. So we can solve this problem algebraically.
One method that works to solve systems of equations is algebraic substitution. Algebraic substitution makes logical sense. It means you solve the first equation for one variable in terms of the other, and then substitute the obtained value into the second equation. Show them what I mean, deviants. You'll soon find out that the answer to this algebraic nonsense is instant breakfast.
Using our example of Bad MacDiver and his store, first we want to solve the first equation for one variable in terms of the other. It doesn't matter which one we use, either will work. So if we solve the equation x plus y equals 90 for, say, y in terms of x, we get y equals negative x plus 90. Notice that this is the same y-intercept form we used when we drew the graphic solution. Now we can just substitute the solution for y that we just obtained into the second equation, 3x plus 2y equals 230. We know y equals negative x plus 90, so the second equation must be 3x plus 2 times the quantity negative x plus 90 equals 230. Simplify to 3x minus 2x plus 180 equals 230, and x equals 50.
Remember, we're on video, so if you ever want to see one of these math tricks again, simply press rewind. Simply press rewind.
To find the other variable, we can plug x equals 50 into either equation, say 3x plus 2y equals 230, and simplify to find that y equals 40. Again, we confirm that MacDiver purchased 50 packs of bubblegum and 40 boxes of Band-Aids to begin his business.
Hey, fool! I need bubblegum and Band-Aids!
Work's been pretty slow since the A-team, huh?
You telling me? But I've got an audition for the lead in the musical. It's called Annie.
A second way to solve systems of equations is called algebraic elimination. Elimination is a fundamentally different strategy than substitution. Through substitution, you lose a variable in one equation effectively by replacing it with a whole other equation. Look at the last example. You take the first equation, x plus y equals 90, put it in terms of y equal to negative x plus 90, then basically stick the whole thing into the second equation. Elimination is different.
Here's the deal with elimination. What you want is a match of variables. You want two variables in the equations to match so that you can add or subtract the entire equation and eliminate a variable.
Okay, take another look at our two original equations, x plus y equals 90 and 3x plus 2y equals 230. Our objective is either to eliminate the x value and solve for y, or to nix the y and solve for x. You can see that if you were to add a negative 3x to the positive 3x from the second equation, The result will be certain elimination of 3x. Likewise, adding negative 2y would make the positive 2y disappear. Either one works. The choice is strictly up to you.
So, let's get rid of the x then, shall we? First, we'll multiply our now familiar first equation, x plus y equals 90, by negative 3, on both sides, of course, to maintain equilibrium. And we get negative 3x minus 3y equals negative 270.
Multiplying by negative 3 gives us negative 3 times x plus y equals negative 3 times 90, or negative 3x minus 3y equals negative 270. Now, add this equation to the second equation. The easiest way to do this is to set one equation over the other and add term by term. You can see the result. 3x plus negative 3x equals 0x, so that x disappears, as we planned. 2y plus negative 3y is negative y. And 230 plus negative 270 is negative 40. This gives us negative y equals negative 40, or y equals 40. Well, now that we have a solution for y, we can plug that 40 into either original equation in order to find that x equals 50. Once again, through elimination, we have shown that MacDiver purchased 50 packs of bubblegum and 40 packs of Band-Aids to begin his business.
In our MacDiver example, the first step was to multiply the first equation by negative 3 to produce a match of the x coefficients. So the two canceled out when added. You should know that you also could have multiplied by positive 3 and just subtracted the results. It's the same operation. However, this worked because the first equation's x had a coefficient of 1, so it's easy to just multiply by 3. What can you do when both equations have coefficients that are not 1? Here's a new example. We've got 5x plus 6y equals 10, and 3x plus 4y equals 8. You can't multiply by the same number to produce a match. It won't work. So we've got another trick for you. Multiply the equations by different numbers that produce a match. For instance, multiply the first by 2 and the second by 3. You'll get 10x plus 12y equals 20, and 9x plus 12y equals 24. Then subtract, and you eliminate the y to get an x of negative 4. Wow, cool, huh? You could also eliminate the x in this problem by multiplying the first equation by 3 and the second by 5. This gives you 15x plus 18y equals 30, and 15x plus 20y equals 40. Producing a match in the x's. Subtract, and you eliminate x, and are left with a y of 5. So to sum it up, in this method of elimination, your goal is to produce a match of one of the coefficients so that when you add or subtract the two equations, you eliminate the variable. And you can do this by multiplying the equations by any numbers that will produce a match.
Item. You can use either substitution or elimination to find an answer to any system of equations. Next issue, inequalities.
Section B, solving systems of inequalities. Now, let's throw a wrench into the works.
Here's a little hypothetical example for you. What if MacDiver had not seen our counting tape and was not certain he had used all $90 he had to start with in order to purchase his inventory? And worse, what if he had $230 in the cash register at the end of the day, but another shipment of bubblegum and Band-Aids came in, so he did not know for sure if he had sold out his entire inventory? This brings us into the uncertain realm of inequalities. And you've seen inequality signs before.
Less than, greater than, less than or equal to, and greater than or equal to. These signs are used in relations to identify inequalities. In this hypothetical case, if we are not sure that MacDiver used all $90 to purchase his starting inventory, then we can say that the sum of the number of packs of bubblegum and boxes of Band-Aids MacDiver purchased was less than or equal to 90. This can be written as x plus y is less than or equal to 90. Additionally, if we are not certain that MacDiver sold out his entire inventory on the first day, we could say that 3x plus 2y is greater than or equal to 230. How can we use these relations or inequalities in order to come to any conclusion about the number of boxes of Band-Aids and packs of bubblegum MacDiver purchased in the first place? With inequalities, there are typically an infinite number of solutions. For MacDiver, for example, the point 7015 is a solution to both inequalities. So maybe he started with 70 cases of bubblegum and 15 cases of Band-Aids. But 6520 is another possibility, and there are many more. That's why the best way to find the solution to a system of inequalities is to solve the system graphically. It's just easier to use a graph to identify possible values of x and y than to algebraically solve an infinite number of possible solutions.
There is an easy way to graph linear inequalities. First, express the inequality as a regular equation in standard slope-intercept form. Our first inequality is x plus y is less than or equal to 90. First, we isolate the y and put the equation in standard form of y equals negative x plus 90. Then we temporarily swap the inequality sign for an equals sign so we can graph the equation. That line represents all the points where y and negative x plus 90 give equal results. All the points above the line are points where y is greater than negative x plus 90. Those below the line are where y is less than negative x plus 90. Our problem uses the inequality y is less than or equal to negative x plus 90, which corresponds to all points on or below the line of the equation.
Now take the line for our second inequality. Y equals negative 3 over 2x plus 230 over 2. This time y, when isolated, is greater than or equal to y equals negative 3 over 2x plus 230 over 2. So we are looking for all of the points on or above the line of the equation.
Now, let's put the graphs together. First, we graph the linear equation y equals negative x plus 90. But since it's also possible that y may take on any values less than or equal to negative x plus 90, we shade in the region in the graph for values less than this equation. For the second equation, y is greater than or equal to negative 3 over 2x plus 230 over 2, we can graph the linear equation y equals negative 3 over 2x plus 230 over 2. Since it's also possible that y may take on any values greater than or equal to negative 3 over 2x plus 230 over 2, we must shade the region in the graph for values greater than this equation. The solution for this system of inequalities will be any point that falls in the region where both results were shaded.
Any ordered pair in this region will satisfy both of the inequalities. Obviously, for this problem, it would make no sense for x or y to be negative, so we can eliminate the portion of the graph below the x-axis and left of the y-axis. Any combination of packs of Band-Aids and packs of bubblegum represented in this double-shaded region could be the combination of packs of Band-Aids and bubblegum that MacDiver started out with in his store. And like with all inequalities, although we can't determine exactly what x and y are, we can graphically display the full range of possibilities.
Section C. Systems of equations with more than two variables.
We've now seen examples of systems of equations using two variables and two unknowns. We've also seen that there are both graphic and algebraic methods that can be used to solve systems of equations for two unknowns. However, when dealing with more than two unknowns, the algebraic methods work best.
Graphing equations with 3 or more variables can be tricky because you need 3 or more dimensions to your graph, and 3 dimensions can be very difficult to graph on 2-dimensional paper, unless you're some kind of artist or something. More than 3 dimensions, which you would need for more than 3 variables, is virtually impossible to represent visually.
But have no fear. The algebraic methods we already use to solve systems of 2 linear equations can easily be modified for use with more than 2 unknowns. Observe.
To solve any system of linear equations, you must always have at least the same number of equations as you have unknowns. Using either algebraic substitution or algebraic elimination, you substitute or eliminate enough times to reduce your relations down to a system of 2 equations and 2 unknowns. And you know where to go from there. For an example, look at these 3 equations containing 3 unknowns.
If we are given the 3 equations, 2x minus y plus 4z equals 1, x minus y plus z equals 0, and x plus y plus z equals 1, we must reduce these 3 equations and 3 unknowns to 2 equations and 2 unknowns, and solve for those 2 unknowns. We can then use our solution for those 2 unknowns to find the solution to the third. Solving the first equation for y, we get y equals 2x plus 4z minus 1. Now you have a known value for y, which you can insert into the other equations. Plugging this value into the other 2 gives us x minus 2x plus 4z minus 1 plus z, which equals 0, and x plus 2x plus 4z minus 1 plus z, which equals 1.
Simplify the equation on the left. Remember that the minus outside the parentheses needs to be applied to everything within the parentheses. So it's x minus 2x minus 3z plus 1 equals 0. Now switch the 1 over to get negative x minus 3z equals negative 1, or equivalently, x plus 3z equals 1. Simplifying on the right by adding like terms gives you 3x plus 5z equals 2.
Dude, this hurts my head.
Now we have a system like our example before, with 2 equations and 2 unknowns. Solving the first equation for x, we get negative 3z plus 1. And substituting that into the second equation, we get 3 times negative 3z plus 1 plus 5z equals 2, or 4z equals 1. Thus, we know z equals 1/4. Plugging that into x plus 3z equals 1, we get x plus 3 times 1/4 equals 1, or x equals 1/4.
Now we know both of the unknowns for our 2-equation system. X equals 1 over 4 and z equals 1 over 4. The next step is to go back to one of our original equations to get an answer for y. When we solved for y, we had y equals 2x plus 4z minus 1. Plugging in the solutions for x and z, we get y equals 2 times 1 over 4 plus 4 times 1 over 4 minus 1, or y equals 1 over 2. The solution to this system of equations is x equals 1 over 4, y equals 1 over 2, and z equals 1 over 4.
You can check to see if your answers are correct just by plugging the values for x, y, and z into all the original equations.
Sometimes there are cases where there are no solutions to a system. You can see this graphically when your known relations are 2 linear equations that run parallel to each other. Remember, linear equations that have graphs that run parallel have the same slope. If this is the case, then the graphs of the equations will never cross. Since the solution to a system of equations is where the graphs cross, then in the case of parallel lines, there will be no solution.
Parallel lines, like train tracks to forever. Ain't no system solution here, never.
Also, you will see cases where there are multiple answers to a system of relations. We have just seen how there are likely to be multiple answers to systems of inequalities, but we may also find multiple answers to some systems of equations where our relations can be reduced to the same equation. For example, looking at the 2 equations, 2x minus y equals 5 and 4x minus 2y equals 10, both equations reduce to y equals 2x minus 5. They're the same equation and have identical graphs. Thus, any answer that satisfies y equals 2x minus 5 is a solution to this system.
Wow, system's gone. Again, if you missed anything, relax, go back, rewind, review. Our next tape, The Dangerous World of Precalculus Part 2, will cover exponential functions and logarithms. But don't stress. It'll be like taking candy from a baby.
My lolly! Well, that's it for part 1 of the dangerous world of pre-calculus. If you have any questions or if you're still a little fuzzy, then just rewind and watch us again. And if you have questions, comments, suggestions, horoscopes, or gripes about anything in our video, then give us a call at Cerebellum. Our number is 1-800-VCR-REVIEW, and we'd love to hear from you.